In this episode, we're going to talk to the ARC Prize 2025 Paper Award third place winner for a paper called ARC AGI without pre-training. This comes with a $5,000 prize. Very excited to have the author here today. Can you please introduce yourself?
Hey, my name is Isaac, and I'm a second-year student at Carnegie Mellon University, and I'm the lead author of ARC AGI without pre-training. It's been wonderful working on this project, and I'm really excited to talk about it with you.
Great. How do you pronounce your last name, Isaac?
Isaac Liao.
Liao. Okay. Cool.
Yeah.
Before we dive into, your paper and the exciting ideas in there, I guess, just catch us up a little bit on your what you've studied in academia so far. I think you've covered some cool ground. Just what sort of topics and areas have you focused on?
In terms of research, I have some background in optimization, and I've studied a lot on information theory because, as you may or may not know, the sort of thesis of most of my work is surrounding information compression and what it means for machine learning. So I've taken a lot of classes on information theory, tried my hardest to study that up. And so that's where a lot of my inspiration comes from.
It seems like a very promising area, but, and you've had great results with ARC AGI, we're going to talk about. But what made you kind of tune into that as an area for study? Because it does seem like contrary to, scale everything up and all we need is, big data and now RL and whatever to just grow these models to AGI. And here you are thinking, no, this is like compression,
So actually, this is like an interesting story. I think back before all of this large language model stuff became like really big in the mainstream way, I was like a sophomore in undergrad, and I discovered this like Marcus Hutter website, the Hutter Prize for information, compressing the Wikipedia into a short program as possible. And I was like, who would award I forget the exact amount, but it's like some sizable fraction of €1 million, or maybe it was €1 million for compressing Wikipedia text. This makes no sense. I didn't really get it at all. So I was looking into the reasoning behind this, who would pay to compress, and they had a lot of explanation as to why compression was seen as an important challenge that would have a lot of downstream results. And it was regarding the link between compression intelligence. And I didn't really understand it all at first, but I had to think about it for a long time and mull over these explanations and really come up with a lot of thought experiments by myself to try to figure out whether it was really true that compression was linked to intelligence and that each ability could be algorithmically used to replicate the other. And in the very end, I became somewhat convinced enough to try using that principle in order to do some basic experiments, try it out within a class project context. You got to hit two birds with one stone sometimes.
Yeah.
So I did that, and it turned out to be pretty successful. I ended up sort of reinventing decoder side of the variational autoencoder with the loss function. And then a few months later, I read up on some more machine learning literature, and I discovered that this thing actually existed. And it was published in 2014, a variational autoencoder, and there was my loss function. I was like, oh, wow. So maybe everybody else thinks this way too. And over time, slowly, I discovered that maybe that's not the original motivation for variational autoencoders and anything that's elbow-bound and elbow-bound based in general. I became pretty convinced that this sort of way of doing information compression was a very promising direction to do further work in, and that a lot of methods right now hadn't been fully explored in terms of that lens of thinking. So that's what got me into all this information compression stuff when it comes to my machine learning research.
Totally makes sense. I know Francois Cholet has mentioned on Twitter this idea of compression intelligence. And you can think about, any abstraction is essentially a kind of compression of the underlying ideas, right? And that goes for analogy. And it gets real fun when you get into psychology and even language, outside of ML. But that makes a lot of sense, actually. It seems like a pretty rich place to explore. So cool discovery, just even, picking that. I think you double majored in like CS and physics. Is that right?
Oh,
at
yes.
MIT?
I did my undergrad at MIT in CS and physics. It was sort of a bare minimum physics degree. At that point, I was starting to get much more into machine learning research. It was sort of like don't want to be jack of all trades, want to pick one direction and become really good at that. So that was machine learning for me. But I do retain a lot of like knowledge from physics from my training. And in particular, like one of the things I'm the most proud of is I'm not like really afraid of doing long mathematical derivations anymore. So things like deriving the KL divergence between two Gaussians, things like that, like I'd be very familiar with. And if it took me like 3 pages, I'd be like, yeah, no problem.
Wow. That's pretty cool. I like that crossover too. It's neat to be inspired by things, but it's also cool that you chose to focus and sort of have a niche. Was that sort of like a career decision or just like, no, there's an infinity of things to research and look at. Like I'm going to make the most progress if I sort of pick one.
It was mostly a career-focused decision.
Yeah.
I thought that there would be a lot more employment opportunities in the field of machine learning in the future. And well, look at the crazy kinds of opportunities that we have today in machine learning. So,
oh, yeah. This is like golden age for exactly your skill set. I hope you're having fun. It's a bright future for you, my friend. Right before we dive into the paper, we should talk about how you even found out about ARC AGI. I know that we did a ARC Prize university tour where we dropped in at CMU. Maybe we caught you there, but otherwise, how did you first hear about the benchmark?
No, so actually it was way before then that I knew about ARC AGI. I don't remember when I first encountered the data set. It might have been around the end of undergrad, but I was like looking for different kinds of data sets to be applying a compression sort of methodology to. And I was like creating my own sort of custom data sets and like synthetic toy tasks to see if it could recover the sort of structure from whatever like data set that I built, that I would like hide the structure in and see if it would like recover it. And a lot of those like efforts largely failed, but I was still on the hunt for data sets to be trying to recover the data, the structure from. And one of the big constraints was I couldn't really be competitive using a lot of my techniques that I knew of unless I had like a small enough data set that I could like try doing things with like a limited amount of compute and resources. So ARC AGI came across as one of the very like top picks because there's only like 1,000 puzzles in the ARC AGI 1 dataset that are available to everybody to use. Of course, now we know like a lot of techniques now use synthetic data and plenty of augmentations, but it's still largely the same situation where the amount of data is like quite limited, not only in terms of like information content, information theoretically, but also in terms of just the raw data set size as a file.
100%. And that seems like a sweet spot for your compression focus, right? It's like, okay, here's like a very data constrained data set to work with. That makes sense. But also really challenging too, right?
Yeah. Even though there's 1,000 puzzles, I ended up, in the ARC AGI without pre-training paper, it ends up being about just like a single puzzle at a time. It's like this massively data constrained focus to the research.
Let's dive in on the paper. It's really exciting. You made a landing page for the paper, which I'll link to in the YouTube description in the show notes. And people should definitely go check it out because you did a wonderful job there. And definitely read the paper. That should be the obvious call to action to everybody. It tries to come up with a solution for ARC AGI with no pre-training, no data set, no additional data set, and no search, which is kind of like, okay, seems like nothing could be possible there, right? But here comes along your invention, CompressARC, which operates without any massive pre-training, relies entirely on inference time learning, and I think this is like the big star of the show. So can you introduce and give us a kind of high-level view of what's going on there?
So a long time ago, some researchers introduced this minimum description length principle whereby if you could find the shortest program that is self-contained that would like print out the data set, then likely any sort of missing parts of the data set would be filled in with the correct, the so to speak, correct solutions or reasonable infilled patterns. And this has long been like a very theoretical direction. You can read all about it. It's like textbooks and papers from like the 1970s, 1980s. You've got algorithmic information theory and all this stuff going around. And then after that, machine learning didn't really connect very well with this because a lot of the algorithms that were proposed in that field were they wouldn't run in a reasonable amount of time. So if you've ever heard of code golf, it's a very similar task. Code golf is sort of this like recreational sport where you try to write the shortest program that outputs some or performs some task. In this case, we're going to be outputting an ARC AGI puzzle. And really, CompressARC is a code golf innovation where we're using a neural network. We're training a neural network on the puzzle data. We're trying to overfit it to the puzzle data in order to compress the puzzle data into the neural network weights. And then you can hard code the neural network weights into the program to reproduce the puzzle and be able to output it with the correct solution. And this is hopefully more cheap than encoding the entire data set as a whole. So this is the primary motivation behind CompressARC. And it's really this theoretical generalization capability that comes from the old theory of minimum description length and Solomonoff induction that transfers over to the ARC AGI domain and enables the impressive generalization that CompressARC is able to achieve by only training on one puzzle.
What a cool insight and discovery, and taking a kind of existing idea and running with it to create new ideas. I guess one surprising thing, though, is that it works. Like, what were the results of this sort of CompressARC? Like, can you tell us something about the scores?
It gets like 34% or so on the training set. And it's not trained on a training set. This is taking the existing algorithm and just applying it to each puzzle in the training set. And it just solves like 34% of them. And then I do the same thing with the evaluation set, and it gets 20%. This is ARC AGI 1, by the way. And we tried this on ARC AGI 2 on the evaluation set, and there's 120 puzzles, and I think it got around 4.17%. I think this was on the leaderboard for a while, but for some reason it disappeared from Kaggle due to maybe some technical difficulties. But it was getting 4.17%. I submitted the notebook a few times. It was the best of 5. So it was able to have like some non-trivial generalization to ARC AGI 2. I guess I would call this generalization because it's like, it was generalizing from the train set to the test set or to the eval set on ARC AGI 1 anyway. So it's just the same kind of transfer of the same algorithm from the training set to the ARC AGI 2 eval set on Kaggle.
That makes sense, and pretty cool results coming out of that initial insight. I guess, when did you know that you took this kind of MDL idea and ran with it? Like, when did you know you had something interesting? Was there a moment where you were doing some experiment and saw that there was like some promise there, or did you just stick with it and eventually find something?
The process of experimenting with like MDL-based algorithms is quite different than I think a lot of other machine learning, because in a lot of other machine learning, you see like you're measuring the loss and the accuracy and a load of different numbers, and they all correlate with each other, but you're not really sure which one's the right one to look at. And there isn't really like anybody who's telling you that if this number is better, then it's obviously the right decision. But when you are doing something that's based upon compression and you're thinking about Occam's razor, the literal bit length, which is literally the loss of the algorithm, if it's better, it just means your algorithm is smarter. So that's just a very clear signal. When I first realized that this would be like a valuable research direction was when I was doing that class project in sophomore year of undergrad, where I sort of reinvented like the variational autoencoder decoder part. That was like a really formative process for me because I was taking data sets that were encoded to like just raw data sets with like full bit depth images, uncompressed. And I'd be compressing them with my loss function, measuring the number of expected bits in the compressed representation. And I'd see that it would be lower than the raw number of bits, although I could never beat like algorithms like PNG with like my basic machine learning knowledge back then. The information theory was showing that it would outperform just the raw encoding, which means that there's something to this, that I'm doing better than just random. And there's something to be studied here that I'm not really completely familiar with. But more importantly, that this thing might have been like somewhat scalable to the degree that I could actually do a machine learning project on it. And it wasn't just a figment of like 1970s, 1980s theory of all just algorithms that can't be run in a reasonable amount of time.
Was your paper part of, your study? Like, was it part of a thesis, or was it just something you did, as a side project?
No, it's just a tiny class project. It was
okay.
Yeah, I was taking a computer vision class, and they just had an open-ended project where you could propose doing whatever you wanted. And I just proposed like, well, let me try to compress images using like some form of like rudimentary like arithmetic coding or like relative entropy coding style thing. I think I used some version of rejection sampling index coding back then. I didn't know that there was like a name for it. So it's a little bit of reinvention there. Maybe I needed to read more on the literature, but
or not, or kind of approach it from first principles. Especially, we're in a different world now than when those ideas kind of first came about. So there might be new insights to be had there.
They're definitely still coming in. I know that relative entropy coding is like an active research direction that there's been people studying and publishing new algorithms on. So I've been like focused, looking towards that field and waiting for the right algorithm to come out that can be transferred over. It would be a very opportunistic thing.
So this class project was kind of how you got here. How much time did you end up spending on this paper?
I spent like 2 months writing it up, maybe 2 to 4 months doing the actual research. But I'm a slow writer, so writing the blog post it took me about 2 months, and also I hadn't figured out like the best way of explaining the idea yet. Actually, explaining my paper / blog post has been like one of the most challenging aspects of my work so far, and it's an active ongoing thing where I'm trying to refine my explanation of like how ARC AGI without pre-training works and what compression really means in machine learning. And I've worked very hard to talk to many people and repeatedly explain things over and over again and try to test various ways of explaining it and find a way that sticks the most. And I'm currently writing a paper version of this, which I submitted to the ARC Prize paper track, which I guess is what has gotten me into the third place right now.
Is that paper not published publicly yet?
It kind of depends what you mean. I have an archive release coming soon with a slightly improved explanation.
Okay.
But
okay.
Yeah, the version that's submitted is actually currently available on my website. There's a PDF link from the blog post where you can see the same paper.
Everyone should definitely go check that out. I think you're doing a great job at explaining it, but I understand what you mean. Like, there's an art in explaining complex ideas simply and concisely, and it's probably a forever process. I don't think anyone ever will, perfect that. But it's a wonderful pursuit because it means your idea will reach more people, have greater impact and sort of just reception.
Exactly. That's what I'm hoping for.
So let's dive into some technical details of the paper. Here's one, how does CompressARC make the discrete description length differentiable for gradient descent optimization?
So this is a common tipping point. There's a continuous variable that you want in it. So let's say that you are trying to code golf a program and shorten its description length, but there is like some sort of place in the program where you require having some continuous variables, like let's say neural network weights or inputs to the neural network, which both occur in my method. The problem with having continuous valued items in your program is that hard coding them would take an infinite number of bits. So that's not really possible. So you can think of various things like, well, how can I store this? Like, can I have an approximation of it? And that can be like quantization. That can be like various different things. But the thing that I chose is you have some distribution that you pretend you've sampled this variable from. You don't really control the variable that comes out of the sampling procedure anymore. But what you can do is equivalently control the variable that emerges by manipulating the seed. Seed manipulation, we all frown upon it, right? Seed manipulation, this smells like academic fraud, very funny.
Wow. Bold.
Well, the point of seed manipulation in ARC AGI without pre-training is to allow us to have some optionality in the random variable that we choose. And it turns out that if you inject information into the variable that's picked by the random number generator via seed manipulation, you can get the same amount of uncertainty in that random variable as you would have gotten by quantization or any other method. It's all optimal in terms of like entropy perspective.
When you said it was like a hot topic or debatable thing, or you said it's a sticking point, like what are you referring to? Like, did you get some feedback that there was sort of a question there?
Oftentimes when I would explain ARC AGI without pre-training, this would be an area of more difficulty where it's generally like a little bit more unfamiliar territory for machine learning people because it's very heavily into the information theory side of things. So in information theory, you think of a KL divergence as this sort of thing where how many bits does it take to specify a sample from distribution P if you're actually sampling from distribution Q. And so the interpretation of manipulating the seed of a sample from distribution Q in order to get something from distribution P, it intuitively makes sense. That's the main interpretation that I think of whenever I think of a KL divergence. I've used that in all of my studies. I use it to solve like any kind of like homework problems, any sort of studies that I do. And it really eases things up. I don't have to rely on very abstract notation anymore to solve things. But this is the mainline interpretation that I use in ARC AGI without pre-training, where in order to encode a continuous value, I sample it from a distribution and measure the amount of information I have to inject into that distribution to obtain the sample that I desire. And the more information that I inject via putting more bits in the seed, the more accurate I can have the sample be, the less noise there will be in the sample, and I can specify to more bits what the desired sample should be. But this is also like very unrestricted. I can also put 0 bits or half a bit. Many people haven't heard of what it means for there to be half a bit of information in an item. But this sort of makes sense from the information theoretic perspective. You can have like 3.5 bits if your seed is e to the power of, or I guess 2 to the power of 3.5. And what 0 bits means is you're just getting a random sample from the sampling distribution and there's no information at all.
Professor Isaac, wow, I'm learning a lot here. Thank you. This is some pretty deep stuff. It's pretty cool. Okay, another kind of deep dive question. In the paper, you described the architecture for CompressARC being a bit like heavily engineered, but that kind of seems a little bit like at odds with the sort of MDL mission of sort of finding the simplest program. Like, are those things at odds? Is there something to reconcile there?
There is sort of something to reconcile there. If you think about trying to compress one puzzle on its own and writing the shortest possible program in order to print that one puzzle, you wouldn't think of like generating this like massive architecture and then sticking it into the program. The architecture description itself is going to take up so many bits that it's not really going to be a sensible solution. And that sort of breaks the idea of, well, let's try to code golf the data set or code golf the puzzle, and that's what's going to solve the puzzle. The reason that we're trying to code golf each puzzle is because this happens to be our way of code golfing the entire data set as a whole. If you think about code golfing the entire data set, you want a program to print out the entire data set. And we just happened to pick a program that's structured so that it's split up into trying to print each puzzle individually and generate them all individually, independently. You might be thinking that we have to include the architecture in every single program description. But if we try to compress the data set as a whole rather than each puzzle individually, then you only have to define the architecture once at the top of a code, and then you just have to call it over and over again. So the architecture description is actually, in some sense, like 400 times cheaper than the description length that is caused by any individual puzzle, because there's 400 puzzles that you're trying to evaluate at once, but you only need to write the architecture once in a massive program. So it comes from the perspective of trying to code golf the whole data set and the way we've decomposed it into code golfing individual puzzles.
Yeah, that makes a ton of sense. That absolutely summarizes why it works. But that advantage of just having it be once in there, and then every puzzle needs to be. I'm not saying this well, but you said it well.
And it also gives you freedom to engineer the architecture in order to be more conducive to puzzle solving. So it's like you're designing the shortest possible program. Some parts of it are going to be learned, but if you happen to know the parts of the program that would be the best to use to code golf ARC AGI specific puzzles, then you might as well just put that in the program structure to begin with and not have to search over it. When you're trying to code golf the data set, I'm not looking at this from the perspective of, I want to have a network that has transferable skills. Let me try to put minimal assumptions into it. I'm looking at it from the perspective of, I'm trying to minimize the description length of the data. Let's do as much engineering as necessary in order to get the smallest possible description. I'm trading off the description length of the architecture to reduce the description length of the puzzles.
Absolutely makes sense. Another interesting facet of CompressARC, you bumped into like specific limitations, like inability to perform operations like counting or detecting topology or topological properties, rather. Are those, observed limitations, like, are they due to the like constraints of the current like architecture that we were just talking about and its layers, or is that like maybe a fundamental restriction with MDL? What are your thoughts there?
It's definitely not a fundamental restriction from MDL. The way that I developed the architecture in CompressARC is I started with like a very minimal architecture. Granted, I did have the multi-tensor stuff in there already, but I was just trying to puzzle number 42. It's like the simplest puzzle. I just trying to solve that over and over again and try to tweak the architecture. I had a very minimal number of layers, and all the other puzzles I wouldn't be able to solve because they'd have like these sorts of operations that my layers did not have an inductive bias for. So I really started with like the inability to solve all these different puzzles, but with the knowledge that with compression, I could eventually like compress it out and it would be solved only if I had the right layers. So I had trust in the compression procedure to begin with. And what was to remain was to engineer a bunch of layers that would have the specific inductive biases that would be required for solving different puzzles. If you go into the details, I have like this direction axis in the multi-tensor, and that thing is just completely an engineering decision to deal with the fact that a lot of puzzles had like diagonal lines and horizontal lines and stuff like that. So the layers are really conferring different abilities to the network that I assume by default it doesn't have. And so since I wasn't able to find a good parameterization of some sort of convolutional layer to do shape copying, that's why all the shape copying puzzles couldn't be solved. And all of the ones that involved extending lines that went in cardinal directions were much easier.
Yeah, absolutely makes sense. It begs the question, like, where do you think you go next with it all? Like, would you just keep going and having, other aspects of the solution kind of solve for those limitations as it is currently and believe in compression, as you said, and, come up with more aspects? Or, do you have new ideas that you're looking to explore? Where do you go from here?
When it comes to trying to engineer more layers to confirm more abilities, it's not like we're going to enumerate all the possible abilities that are required to solve At that point, like you're just manually searching. It sort of boils back down to the idea of like, let's just search all the programs for the smallest program that will solve the problem. I mean, it's more targeted than that because you're engineering, you're looking at puzzles, and then you're like thinking like, what kind of layer will have an inductive bias? How do I pick the initialization and such? But it's quite clear to me that that's not really a scalable way to continue and develop like better intelligent procedures. So something automatic might be the best when it comes to that. Or I'm thinking about things like using attention, so tokenizing all these different things and having a puzzle embeddings, color embeddings, row embeddings, column embeddings, augmentation embeddings, and just throwing it into a big attention operation and seeing if that could potentially learn things without still have the right inductive biases to fit the puzzle data. But of course, naturally, if you increase the flexibility of the layers in a network, you're much more prone to overfitting. There will be more weights in the network and the description length will be longer, and you're less likely to recover the correct solution. I still think that this is a reasonable direction because other people in other works have gotten transformers to work very well on ARC AGI. Granted, they do need much more training data. I still think they have reasonable opportunity to solve one puzzle at a time. And that's also an artificial restriction on our part that sort of came in the end, where we just happen to be solving one puzzle at a time. So it's like, well, might as well market the paper and a blog post this way. So I guess shout out to hierarchical reasoning model and tiny recursion model. Yeah. Shout out to Agar.
Yeah, shout out. Actually, Alexia won the first place prize for the paper award this year. And I just talked to her a couple of minutes ago.
Oh, congrats to Alexia.
Definitely big shout out. Those are some ideas as to, like next steps. You're in the middle of all kinds of stuff. You've got, your academic studies, probably all kinds of side projects. You've got the rest of your life to deal with.
Oh, tell me about it.
Do you plan to keep kind of pulling the thread here and keep exploring ARC AGI? Do you have new ideas to try?
Not as much. Right now, my main focus has been, you may or may not have noticed from the blog post that I did all my research on ARC AGI with one GPU. This is in part because I don't really know that much about how to scale up like machine learning systems. So I'm right now focusing on learning all of that stuff, getting used to various libraries and ways of organizing models and training runs and putting all of the processes together.
Oh yeah, you're going to learn this fast. I can tell.
Upskilling for me.
Yeah, but that's going to be a great resource for you, like a great thing. There's a great community around ARC AGI. Like I think you should shout it out if you ever need anything. Just encourage anyone watching, please like get into Discord and ask questions. There's going to be somebody who will have already bumped into the whatever trouble you're running into. Is there anything in machine learning that you've observed that is not obvious that's worth sharing with everybody?
I think a lot of architectures and loss functions that people have been using that have become successful over time are implicitly like compressive loss functions that you could equivalently derive through the same kind of reasoning about seed manipulation and sampling procedures. If you actually take like the loss functions for any elbow-derived architecture, anything that consists of a sum of KL, divergences, cross entropies, mean squared errors, you can write that out in terms of that's like the length of some program template that is trying to be code golfed. And the training algorithm that you all know of is actually an algorithm for minimizing the length of that program implicitly. But that's one way of looking at it. That's not the way that it's generally presented, but actually a surprisingly large number of algorithms fall in this class. So autoregressive models that are trained on cross entropy, you can even have regularization on them and it will be accommodated by this explanation. Diffusion models are actually derived from elbow bounds, so they all fall under this category. I saw this recent free transformer by Francois Fleuret that would be derived from like an interesting different kind of program structure that also wants to be minimized in terms of description length. And variational autoencoder, of course, maybe a number of other things that I haven't mentioned. Some kinds of Bayesian neural networks fit in this class too. This is sort of my motivation for using the compression methodology to derive new algorithms. It's that maybe I can write new kinds of template programs, calculate the expected amount of description length that they take up, and then write a new kind of algorithm that minimizes that. And that's my sort of like secret sauce when it comes to my research.
Any advice for folks who are looking at ARC AGI and going, this is like way too hard? I'm not sure even where to, attack the problem from. Like, do you have any sort of advice for people just getting into this world?
I'd say there's like a lot of like maybe fringe ideas that are out there that people have been talking about for solving ARC AGI. And then there's like a sort of mainstream cluster of ideas surrounding large language models, and just like taking that and just turning it up to the max. Both of those things are valuable. I wouldn't discount the sort of fringe ideas that have been out there, because maybe this is a bit of my own bias, because I've been working on a fringe idea, but I think there's good headway to be made by working off of those ideas. There's been an increased focus on recursion recently. I'm a big fan of it. ARC AGI without pre-training doesn't use it, but I've been sort of following that kind of work. HRM and TRM are included amongst those. It's one of those domains where there's a lot more value in independent thought rather than just following the flow and trying to do what everybody else is doing. And in fact, I think this is like one of the original reasons why ARC AGI was originally created. It was to try to get people to think of new ideas and new ways of solving different problems. Sticking to that philosophy, I think, is a good thing, and it will lead you to places. And that's what led me here.
That is an amazing note to end on, Isaac. Just huge congratulations for winning third place in the paper prize. I think this is just the beginning of things we'll be hearing about your illustrious career going forward. So happy to be here for the journey and can't wait to see what you get up to next. And thank you for taking the time to chat with us.
Thank you for having me on.